Ever wonder why some things shine while others break so easily? Welcome to the world of metals and non-metals. Let's discover their secrets. You will be
Look at the
amazed.
sheer force it takes to shape an iron block. You need extreme heat and a heavy hammer to make it bend. For most of human history, figuring out how to dominate stubborn elements like this was how we expanded our cities, fought our wars, and built our infrastructure. Which brings us to a historical anomaly. This is the Iron Pillar of Delhi. It weighs over 6,000 kilograms, and it was forged during the reign of Chandragupta II, over 1,600 years ago. You would expect an iron structure left exposed to wind and monsoon rains for 16 centuries to be a crumbling heap of red dust, but it's barely rusted at all. It stands completely intact. To understand the metallurgical chemistry keeping this pillar intact, we have to look at the specific physical boundaries that separate all earthly materials into two distinct kingdoms. The first rule is about physical stress. When you hit a metal like copper or iron with a hammer, it doesn't break. Instead, it absorbs the impact and flattens out into thin sheets. We call this property malleability. But try applying that exact same force to a chunk of coal. It shatters instantly into dust. Coal, along with sulphur and wood, belongs to a group we call nonmetals, which are entirely brittle. Metals possess a second physical superpower called ductility. This means, instead of snapping under tension, they can be drawn out and stretched into incredibly long, continuous threads. You see this in action every time you look at thick spools of copper wire waiting to be strung up as electrical lines. Because metals can be hammered into flat panels and stretched into miles of cable, they form the literal scaffolding of the modern world. If we tried building bridges or skyscrapers out of nonmetals, they would simply crumble under their own weight. Resistance to physical impact is only half the story. The other defining boundary involves internal energy transfer, a process called conduction. Deep inside a metal, atoms are packed in a specific way, allowing heat and electrical currents to race freely from end to end. But when that energy hits a nonmetal, it hits a roadblock. It is absorbed and instantly halted. This is exactly why we build the handles of our cooking pots out of wood, or wrap our power cords in thick rubber. They are poor conductors, acting as deliberate barriers to those intense energy flows. Metals allow us to move heat and electricity across vast distances, but without nonmetals to act as insulators, we wouldn't survive the process of actually using that power. Yet, for all their physical toughness, metals hide a massive, invisible weakness. They are highly vulnerable to chemical attacks from the air and water around them. When certain metals come into direct contact with oxygen, they react violently, burning with a blinding white flame to form a powdery basic oxide. Most metals don't react quite that fast, but they face a slower, more creeping threat. When iron mixes with oxygen and moisture, it triggers a gradual deterioration known as corrosion. We know it as rusting. This slow chemical burn literally eats right through the iron, hollowing it out and destroying the exact physical strength that made it useful in the first place. It's a constant battle. The strongest materials we have are locked in a perpetual state of chemical decay. To build anything that lasts, we have to find a way to outsmart nature itself. Which brings us back to the Iron Pillar of Delhi. The fact that it still stands today is proof of a highly advanced ancient mastery over these exact chemical rules. By engineering a precise chemical composition on the pillar's surface, ancient Indian metallurgists shielded the vulnerable iron from oxygen and moisture. That ancient philosophy mirrors how we build the world today. We rarely use metals in isolation. We constantly pair them with protective nonmetals to insulate their chemical and electrical weaknesses. Look at an electrician working on a high-voltage grid. Those thick rubber gloves are a non-metal shield, blocking the lethal conductive power of the copper wires inside the panel. Human progress isn't driven by finding one flawless supermaterial. Instead, it relies on engineering a perfect, lasting harmony between the elements that build and the elements that protect. Outside of industrial engineering, nonmetals sustain the mechanics of biological life. Take nitrogen, for example. It is an essential nonmetal used to manufacture the fertilizer pellets that sustain global agriculture and keep the planet's crops growing. Or consider iodine. When processed into an alcoholic solution, this nonmetal becomes a vital antiseptic used to clean wounds and prevent infections. The dynamic is perfectly split. Metals construct our cities, carry our data, and distribute our power. Nonmetals grow our food, heal our bodies, and protect us from the sheer force of our own technology. We often hear that we live in an age of metals, but the truth is, our entire civilization thrives entirely on our ability to balance the elements.